Hello everyone, and welcome to the series on R programming. This series is going to be useful for those of you who have never programmed in the R programming environment, or have programmed in R before and may have forgotten some of the basic principles, or you may want to possibly figure out or learn some new tricks and tips associated with the R programming language. If you fall into any of those categories, let's get started. As you may already know, the R programming language and environment is mainly targeted at uh, analyzing statistics, doing data analysis, or possibly even doing some machine learning or artificial intelligence implementations. And with all of those things, you definitely need to have a data set in order to analyze. So what I've done already is I've created an artificial data set for us to sort of work through for this video to sort of illustrate some of the basic principles associated to the R language. I've called this data set patient_data.csv, where CSV stands for comma separated values. So if I click this little data set, you'll actually be able to see what type of data I'm actually going to be working with today. So in the first column, I have patient number, systolic blood pressure measured in millimeters of mercury in the second column, age in the third column, height in the fourth column measured in centimeters, and weight in the fifth column represented in kilograms. If you do not have this data set or you want to create your own, you definitely can easily do so. You can create a CSV file in a text document and just save it as a .csv file once you're done creating it. Or you can create this dataset in Excel and just save it as a .csv file. And R also imports some other different types of file formats as well, but CSV is the most common format, so I'm going to be illustrating how to do that today. So the first thing that you need to make sure before we start programming in R is to make sure that all of your environments are clean and your data set is where you need it to be. So notice that our patient.csv file is located down here in the right bottom corner under Files. To make sure that R knows that this is the directory that you want to focus on, just click this little toolbar More, and then go to Set as Working Directory, and then make sure that you have, for example, set WD to be equal to the location that this file is in. Also, if you have anything that is sort of located in this console, to clear that you can just do Control L and that's going to remove everything. Another thing that you probably also want to clear out is the environment. This is where all our variables and things are going to be stored. To clear this, just click this little broom and that's going to clear everything there. And then you have a nice blank R environment to work on. Right? So now that we have all those things, let's start coding in the R language. Just because we have a data set and probably other data sets defined on our computer system, it doesn't mean that R will be able to find it or work with that data. So in order to operate on anything in the R programming language, it needs to be imported inside of the R programming environment. So the first thing you need to make sure, again, is that the data that you want to import is located in the directory that is current and focused on. Then we need to import it into the R environment. If you can't see it in this top right window where it says environment is empty, R can't see it either. So in order to read in that particular data set, we need to use the function read.csv, open parentheses, double quotes, and then the name of your file, and of course this is going to be case sensitive. So my file's name is patient_data, included with the file extension, in this case, is going to be CSV, close double quotes, close parentheses. And let's assume that we're going to be calling this data, let's call it my data. And that little arrow minus sign just means we're going to be assigning the output of this function to this variable my data. Once you have that done, just do Control Enter or click Run, and that's going to run that particular line. If it can find that data set, you should see it appear up here in this environment window, and you should be able to click the little arrow and see a little quick summary of what that actual file actually contains. So if we go back to our actual CSV file that we're going to be working with, and if you created this for example, Excel or text, notice that there are 16 rows, with rows 2 through 16 going to be the patient data, and row 1 being the categories. But if we go over here to the My Data and sort of understand how R reads in that variables, notice it says it has 15 observations of 5 variables, where those 5 variables are patient number, SPP, age, height, and weight. So the first row is always going to be your, I guess you could say, classes or your object names. And it's also very important and good practice to make sure that there are no spaces in each of these names, which is why I have an underscore for the patient number class name. In case you do not want to sort of look at the data in this little window over here and instead look at this data in the console window, we can actually go back over to our program and use the function print. So print, and then the file name will actually display the data in this little console window. So notice here that we have patient number, SPP, age, height, and weight, and the data for each of the values as stored in our SV file. Sometimes it's a little bit easier to look at in this little window. Another alternative to displaying and also storing data, and this is going to be the more common way that we're going to be doing things, is to be creating what we call data frames. And data frame is just sort of like a box of data, including titles and the numbers and the structures and all that stuff. So our data frame is going to be called df1, and you can call this data frame anything you want, just make sure there's no spaces in the name. And this is going to be equal to data.frame, that's the function name, and then the data that you want to sort of create or store as a data frame, which is going to be called my data. So once we define df1 to be our first data frame, notice that again, once you run that, it does come into our environment, and that's going to give you your class names and your class values. And you should be able to notice that as we imported our data, they practically have the same exact structure with minimal to no difference, right? But keep in mind that a data frame is just a more classical way of structuring the data, and most of the R functions are actually going to prefer you to have everything's saved inside of a data frame. So now let's look at a couple functions that you probably definitely should know how to do when you're analyzing data. So let's assume that this data set over here, in particular df1, contains, for example, several different columns, several different rows, and we don't want to know all of them. We just want to know, for example, the categories of those columns, right? The category names. In our case, that's the systolic blood pressure, height, weight, patient number, and so on. So to look at the names or the names of the classes for our data set, which some people also call headers, we can just use the names function. So names, my data, or names of df1 is going to display the names of your data frame or your data set. So the categories in our data frame are patient number, SPP, age, height, and weight. So if you want to access only the systolic blood pressure values, what you can do is you can do df1 $, and then whichever class you want to display. So for example, if we're interested in doing age, we can do df1 $age, and that's going to display all of our ages as a vector. We can do, for example, df1 $weight, and that's going to display the weights as a vector. And we can do, for example, the patient's systolic blood pressure. That would just be SPP after the $, and that will allow you to access practically any class within your particular structure. Again, although environment window does summarize your data, for example, how many observations and how many variables you have, sometimes it's easy to sort of store those variables in some structure again. So what would the dimensions of our data set be? Well, we have 15 rows and 5 columns, where those 5 columns are corresponding to the headers located in our pseudo row number 0, right? So it's technically row 0 through row 15, which is the same as row 1 through row 16 in Excel. So ddata, the dimensions of our data, can be accessed via the function dim of the data frame that you're interested in. In this case, this is called, for example, my data or df1. So if we run that, notice that we have an integer vector, which is going to be 15 by 1. So 15 rows by 5 columns. And if we want to sort of store those numbers for whatever calculations that you want to do a little bit later on, what we can do is, for example, assign MD to be equal to the number of rows, right? So this is going to be the number of rows. And everything that's sort of following after a hashtag sign is going to be a comment, so R can't see those things. So you can literally plug anything after those little symbols, and it won't make a difference. This is just so that you can sort of organize your code. All right, so this is the number of rows, and this is going to be the number of columns. So how can you get the first element of this particular vector? So this is going to be equal to d data, the first element, or the first output of that particular function. And then here we can do, for example, d data, the second output. Right? So that's going to assign 15 because that's the first element of this vector 15, and nd should give us the number of columns in our data set, which is going to be d data comma 2. You can also put a bracket after the end of the dim open close parentheses function directly without having to save the d data variable, just to sort of save you some room, but these are some of the cleaner ways that you can actually do the same exact thing. So up to this point, what we have is the dimensions of our data set, which is a 15 by 5 matrix, I guess you could say, with the matrix having MD, which is 15 rows, and ND, which is 5 number of columns. And those are some of the basics that we definitely have for importing and analyzing the size of our data set. Now that we're able to analyze the size of our data set and also observe the values that are located in our data set and what they actually are, now let's see if we can sort of extract some rows and some columns, more over some subsets of our data set, so that we can analyze them directly without having to look at all of the other values. So let's assume that we want to extract the first row of our data set, and the first row I'm going to call row 1. Now when I say row 1, I'm not going to talk about the first row that contains our headers. I'm talking about row 1, which is going to take the first row of our data set, which is going to be row 2 of your Excel file. So in order to extract row 1 with all of the columns, what we can do is we can call our data set and select a subset of it. So what we want is going to be the first row and all of the columns. So it's going to be the first column through the last column whose index is ND, which we've already determined to be the number of columns in our particular, in some sense, matrix. So that is going to store all of the values of row 1 into a vector called row 1. And if we just sort of display that, notice that that does display patient 1's information: blood pressure, age, height, and weight. So for example, if we want to look at, for example, row 7, so let's define a new vector called row 7. So again, my data. Now this is going to be row 7, and again, all columns. And if you don't want all of the columns, you can change that, of course. But that's going to create a new vector called row 7, and then we can display the vector called row 7, which is the information associated with patient number 7, which its information same as above. And again, in terms of the syntax, we're looking at, so before the comma, that's the row number or numbers that we're looking at. And then the second thing after the comma, that's going to be the column number or the column number range that we're going to be looking at. Similarly, we can look at the columns that we're interested in. For example, let's assume that we're looking at column 2. So column 2 is going to be equal to my data. So here we're going to be looking at all rows, second column. So all rows, that's going to be 1 to MD, which is already defined above as the number of rows in our data set, and the column or columns that we want. And we just want column 2. So if we sort of display that, that will also display it also as a row vector, although it's associated to a column, but it's a vector nonetheless. And of course, if we want, for example, to be column 4 is going to be equal to not patient number, SBP, age, but that's going to be equal to height. So we can do my data, all rows in the 4th column, and then display column 4. That's going to be equal to all of the heights for all of the patients in our study. Now there are some better alternatives for column data because columns are associated to classes in our data structure. So for example, what we can do instead is the following. So for example, let's assume we want to store the age values associated to the my data set. What we can do is we can again call our my data set and look in that structure for the category that is the age class, which is encapsulated inside a double bracket. So if we do that and then do college age, that's going to display the ages of all of our participants. And for example, we can do a similar dim, for example, the column associated to the systolic blood pressure, and that's going to be again my data, open, close, and then we can do, for example, SBP and double brackets. Now, again, there is another alternative that's maybe even more clever than this. And what we can do, but instead of doing, for example, COL SBP, what we can do is, for example, COL SBP and define this to be equal to my data and then $ SBP. So that's the SBP class associated to my data. And for example, if we display COL SBP, that's going to give us all of our systolic blood pressures associated to our patients in our study. A common transformation that people usually want to do to a dataset is to display things from least to greatest or greatest to least. Let's assume that you want to go from the least to greatest fashion of your dataset with respect to the variables systolic blood pressures. So in order to do that, we first need to get a permutation vector that will rearrange our dataset for us from least to greatest. In order to get that permutation vector, you need to get the function order and then perform that on the vector that you want to sort with respect to. So I'm going to call the output vector SPB indices. And this is going to give us the permutation vector that is going to allow us to sort our vector from least to greatest. So the function that is going to help us generate that permutation vector is the function order, and then the vector that you want to supply order is the vector that you want to sort with respect to. So let's assume that we want to sort our data set with respect to systolic blood pressures from least to greatest. So that's going to give us our permutation vector, and you can look at our permutation vector here, which is going to be a bunch of positive integers that is going to tell R how to rearrange your data set. So then, once we have that, then we may want to, for example, display a new data frame that is going to contain, for example, our patient numbers and their systolic blood pressures listed from least to greatest. So the first category, or our first class, is going to be called patient. And the values in the patient category are going to be equal to my data, $, the patient number, but we're going to be sorting these things, in particular the things in my data $ patient number. We're going to be sorting them with respect to the permutation vector SBP indices. That's the first column. Then the second column is going to be systolic blood pressures. That's going to be the name of the second class. And that's going to be equal to my data, systolic blood pressure, but we want to sort them with respect to our permutation vector. So again, we're going to do SBP indices. And then it's going to create a new data frame that contains those two classes, patient number and systolic blood pressure. So if we look at our data frame, that's going to give us our patient number and the systolic blood pressures listed from least to greatest. Let's see if we can perform a couple little calculations on our systolic blood pressures. For example, let us assume we want to, for example, count the number and also get the percentage of individuals with systolic blood pressure larger than, let's say, 124 millimeters of mercury. So how do we do that? So what we can do is we can sum the binary vector my data $SBP greater than 124. So what does this vector actually look like? So if we look at this vector on its own, notice that it gives us a bunch of trues and falses. So trues are defaulted by the numerical value 1, falses are defined to be the numerical value 0. So my data $SBB, literal greater sign 124, is just a binary vector with a bunch of zeros and ones. So if we sum up a set with only ones and zeros, then the sum of those values, 1 plus 1 plus 1 plus 1 plus 1 plus 0 plus 0 plus 0 and onwards, is going to give us the total number of people that actually satisfy that particular comparison, right? So the sum of those values is going to give us the number of people in our data set that actually has a systolic blood pressure bigger than 124, in our case 11. Now let us see if we can figure out the percentage of the individuals in our data set that actually satisfy that. So to do that, we're going to take that number. So my data, $systolic blood pressure bigger than 124. So that's the number of values in our sample that has that particular blood pressure, and then we need to divide that by the total number of values of systolic blood pressures that we have. So it's going to be equal to length of the vector my data SBP, and according to this we have 73.3% approximate of our values that have a systolic blood pressure bigger than 124. Now, let's see if we can answer just another question just for fun. Let's see if we can find the percentage of individuals with a height between 150 and 160 inclusive of the boundaries. So 150 and 160 are going to be included in this calculation. So we're going to be pretty much doing a similar calculation to this sum over length type of calculation. And how are we going to do that? So we have two criteria, right? Bigger than 150, less than 160. So to do both of them, we're going to do sum open open, and then my data, and then we're going to be looking at the height category, and then we want all values greater than or equal to 150, and we want all the values in my data $height to be less than or equal to 160. So as long as you satisfy both of these criteria, not one or the other, but both, then you're going to be calculated as a 1 in this particular binary vector. And then as usual, we're going to be dividing that by the length of the vector that we're analyzing, which is going to be my data and height. And that's going to give you the percentage of individuals whose height between 150 and 160 inclusive of the boundaries, which is approximately equal to 46.7%. Now that we know how to sort a data set, and also calculate the number of values that satisfy some criteria, and also how to calculate the percentages of values in our sample that satisfy some criteria, let's go ahead and calculate some common statistics that are commonly used in data analysis. For example, the mean, standard deviation, and a couple others. So the first metric that we're going to be looking at is, for example, the arithmetic mean, which I'm going to be calling SBP A mean. So in order to calculate the arithmetic mean, you just need to use the function mean. And that's going to be my data and the data set that you want in this data set, which is going to be SBP. So that's going to give us a systolic blood pressure arithmetic mean of approximately 129.6. Now let us assume that you want to find the geometric mean. So that's going to be SBP G mean. And as far as I know, there's no basic function, but you can easily create one with no big deal, which we'll do a little bit later. But to calculate the geometric mean, you can do the series of functions exp of mean of the log of the vector that you want to do. So for example, my data $SBP. And that's going to give you the geometric mean, which is approximately equal to 129.4. Let's assume now that you want to find the median, so let's call that SBP MED. That's going to be equal to median of my data $SBP. And that's going to give you the median element of your data set. Now let us do the range. That's going to be the maximum minus the minimum values. So let's do the maximum of my data SBP minus the minimum of my data, and then SBP. That's going to give us the range. Now let's do the standard deviation, SBP STDEV. And that's going to be just SD of my data $SBP. Now, I just want to mention very quickly, this SD function is a sample standard deviation formula, i.e. the sum of squared differences divided by the sample size minus 1, and then the square root. It's not a population standard deviation. So if you want to do a population standard deviation, you just have to do a couple little algebraic manipulations to this to sort of get to the other formula that you actually want. So just be careful that you're not working with populations. If you're using this formula, make sure you're working with samples if you're using the SD function. This is equivalent in Excel to the stdev.s formula, in case you're curious. Now, let's assume that we want to, for example, find the sum of absolute deviations. Let's call that SPB and SAD. So that's going to be the sum of the absolute difference of the value minus the mean. So in order to do that, what we can do is we can do the sum of the absolute value of the vector, my data SBP, minus the number, the mean of my data, and then SBP, but we've actually already called that something. That's called that SBP, and then a mean. So although this is a vector minus a number, what it's actually going to do is it's going to subtract this element from each of the elements of the vector. Then it's going to take the absolute value of each of those elements and then sum up all of the vectors in that value. And that's going to be the sum of absolute deviations for that particular value. And if you want to sort of take the square root of that, that's going to give you something that you can compare to the standard deviation in terms of a measure of variation. And another metric, although there are plenty more, would be for example, the coefficient of variation, which is a metric that doesn't have any units. So in case you don't already remember how to calculate that, that's just going to be the standard deviation of our data set divided by the systolic blood pressure arithmetic mean. And that's going to give you the coefficient of variation, which you can interpret as usual. Now that we have all of these little data metrics for our systolic blood pressures, it might be useful to display all of these in a data frame. So let's go ahead and do that. The first thing that we need to do is define the names of each of our columns in our data frame. Let's call these frame titles. So frame titles, the first column is going to be called A mean, that's going to be for our arithmetic mean, then G mean for our geometric mean, then median, then range, then sample standard deviation, then sum of absolute difference, and then the coefficient of variation. So those are going to be the names of our titles. And then we need to display the values on each of those columns. So let's call these frame values. So that's going to be, again, C, and then it's going to be SBP A mean, SBP G mean, SBP median, SBP range, SBP standard deviation, SBP sum of absolute difference, and SBP coefficient of variation. Now, it's going to display quite a few decimal places when you actually display this data frame. In order to construct or control the number of decimals, for example, let's assume that you only want 3 decimals to be displayed in a data frame, what we need to do is we need to change the formatted number of decimals inside the R programming language. To do so, what we're going to do is we're going to format the values of our frame values vector. In order to do that, we're going to change the frame values vector, and we're going to round all of them to 3 decimal places. And also it requires this little function n small is equal to 3. For default, just set that to be equal to the number of decimals that you plan to round to. And that's going to be rounding all of our values to, notice, 3 decimal places. Now what we're going to do is we're going to create a new data frame. Let's call it, for example, data frame is equal to 3. And this is going to be equal to data.frame of, so for example, we first have the metric, and the metric names are stored in the frame titles vector. And then we have the metric values, so metric values, and that's going to be equal to the rounded version of the frame values equals to 3 is actually another easier way of doing this particular statement, right? Instead of just changing the values, we're just going to display a change values there. So once we have our data frame actually constructed, once we give that a run, that's going to give us our metric values for our systolic blood pressures for our data set. Now there are many other things that you could include and analyze for a data set, but these are some of the basics that you could consider. In the next video, we're going to be looking at some interesting and colorful ways of displaying data and a variety of different graphical displays for data, since this video is primarily focused on just the numerical analysis of those things. So until then, I hope you enjoyed this video. Take care.